All right, initiating diagnostic boot sequence. Welcome to this explainer. When we look at self-driving cars rolling down our streets today, it's incredibly easy to mistake them for just standard run-of-the-mill vehicles that happen to have a neat software patch installed. But honestly, to think of them that way is to miss the magic entirely. These machines are deeply complex, layered engineering marvels. They're literally systems of systems built from the ground up to solve one of the absolute most unpredictable physics problems on Earth: human traffic. So today, we're going to tear down the chassis, so to speak, and uncover the engineering secrets behind how autonomous vehicles actually achieve their safety. Okay, let's dive into this. Here is our schematic for today. We'll be looking at 1. The anatomy of autonomy. 2. Senses through multimodal sensor fusion. 3. The brain and fail operational architectures. 4. Reflexes, specifically real-time emergency maneuvers. 5. The matrix, which is all about sim-to-real bridges. And finally, 6. Building a blueprint for trust.
Section 1. The anatomy of autonomy, peeling back the layers of self-driving safety. To truly grasp the architecture here, we have to look past the hardware and examine the foundational goal driving every single line of code.
Think about this mandate from Waymo's blueprint for safety cases. It's really the ultimate top-level mandate for the entire industry: absence of unreasonable risk. Notice it doesn't say perfect driving. It acknowledges that driving inherently carries risk, right? The engineering challenge is removing the unreasonable risk, the unpredictable human error, fatigue, distraction. Things like taking your eyes off the road to check a text message or spilling hot coffee in your lap. Every single piece of technology we're about to dissect is purpose-built to eliminate those specific, very human vulnerabilities. Moving to Section 2, Senses, multimodal sensor fusion, how AVs perceive the world. Now, we humans navigate the world primarily relying on just two organic cameras: our eyes. An autonomous vehicle, on the other hand, uses a rich, overlapping array of superhuman sensors. It's like a giant puzzle, and these distinct modalities perfectly cover each other's blind spots. You've got radar, a staple since 1999, which is absolutely crucial for tracking velocity and piercing through fog or heavy rain. Then there's LiDAR, generating these high-resolution 3D point clouds for hyper-precise object classification. And finally, RGB cameras for high-fidelity visual details, like actually reading a stop sign. In the past, systems used early or late fusion, which sometimes led to modality collapse, where the system would literally just ignore the weaker sensor. But modern architectures use something called intermediate fusion. By utilizing global transformers like interfuser, they basically weave these distinct data streams into one single, unified understanding of the world. Now, what's really interesting is this staggering number: 450 meters. That is the detection range of Aurora's long-range LiDAR in pitch-black darkness. Think about that for a second. The vehicle is mapping the world in full 3D and identifying hazards nearly half a kilometer away, without a single street lamp in sight. This means the system can recognize a hazard up to 11 seconds faster than a traditional human driver ever could. But, well, seeing far away isn't enough, is it? The car also needs a flinch reflex for sudden, close-up hazards. Enter dynamic vision sensors, or DVS. Unlike standard video cameras that record frame by frame, DVS operates asynchronously. It only registers changes in pixels, so it's essentially tracking pure motion dynamics and edges. And it does this at millisecond-level reaction times, which is, amazingly, far faster than a human blink. It gives the car the ultimate safety net for suddenly emerging obstacles. Section 3. The brain. Fail operational architectures. So, what actually happens when things go wrong? We've got these incredible overlapping senses, but what processes all that data? If an error happens on your laptop, it just freezes, right? But in an autonomous vehicle doing 70 miles an hour down a highway, the internal computer architecture must be flawless. Or, at the very least, it needs to know exactly how to handle its own flaws. And this brilliantly illustrates the concept. When you look at the system architecture for automated driving intelligence, the core AD intelligence is essentially linked to the sensors and actuators, sure, but it is also directly tethered to a diagnostic system. The system is in a constant state of self-interrogation. It isn't just watching the road, it's constantly watching itself, perpetually checking for transient faults or software hiccups. And this right here is a massive paradigm shift in engineering for Level 4 autonomy. Think of a factory robot. If it detects a fault, it triggers a failsafe and just shuts down on the spot. Easy. But a car on a busy highway absolutely cannot just drop anchor and shut down. It must be fail operational.
This means the architecture is divided into isolated fault containment units. If a processor drops completely offline, the system instantly detects the error, isolates it, and just keeps operating safely using redundant backups to navigate the vehicle to a safe harbor. Section 4. Reflexes, real-time emergency maneuvers, or the dual trajectory safety net. Because even with perfect sensors and a fail-operational brain, the car still has to navigate unpredictable real-world hazards, like a distracted driver suddenly swerving into its lane. How does it react? So the crucial point is that a truly safe autonomous vehicle is basically thinking in parallel at all times. At any given moment, the motion planner generates two completely different trajectories. Step 1, it calculates an optimal, comfortable path assuming normal traffic flow. But step 2, it simultaneously calculates an extreme emergency maneuver, a guaranteed safe path to a complete safe stop. The car holds both of these plans in its memory, updating them every single millisecond. If that optimal path gets blocked, it doesn't have to pause to think. It instantly executes the emergency maneuver. To calculate that emergency backup plan, the system uses a mathematical concept called over-approximative future occupancy, which is quite the mouthful. But basically, it doesn't just guess what a human might do next based on probabilities. Actually, scratch that, it literally calculates every single physical space that the surrounding cars could possibly move into, given their current velocity and physics. The emergency maneuver is mapped to steer completely clear of all those potential spaces, guaranteeing a collision-free stop. It's essentially playing 4D chess with physics. Section 5. The Matrix. Sim to real bridges. Crossing the gap from digital to physical. Because how do you train an AI brain to execute these incredible parallel processing reflexes? You definitely can't just put an untrained algorithm on a public street. You have to train it in digital simulation. But bringing an AI out of a video game simulator and into the real physical world requires crossing a massive barrier. We call this barrier the sim-to-real gap, and it's twofold. First is the observation gap. In a simulator, the AI gets perfect, clean, bird's-eye view data of everything. But on the real road, it relies on noisy, flat camera feeds. Second is the dynamics gap. Digital cars don't experience real-world tire friction, heavy cargo weight, or mechanical latency. If you put a pure simulator-trained AI into a physical vehicle, it'll crash almost instantly because of these two specific gaps. To solve this, researchers developed the Sim-to-Real AD framework, acting as a real-time translation layer. It features a geometric observation bridge, which takes a flat, noisy image from a real car camera and mathematically warps it into the perfect bird's-eye view the AI expects. Then, a physics-aware action mapping system intercepts the AI's digital steering commands and translates them into physical, platform-agnostic targets, like curvature and desired speed. This means the AI doesn't even need to know if it's driving a small sedan or a massive transport van. The framework just seamlessly translates the digital intent into physical reality. Let's move to the results and see how this builds out in the real world. Using this translation framework, engineers deployed a simulator-trained AI onto a full-scale Ford E-Transit van. Now keep in mind, this AI had zero prior real-world training data. It was completely zero shot, and yet it immediately hit a 90% success rate in car following, 80% in obstacle avoidance, and 75% at stop signs. By effectively bridging those observation and dynamics gaps, they seamlessly ported pure digital intelligence into a physical machine. Pretty mind-blowing. Section 6. Building a blueprint for trust, proving it works in the real world. So we've got the hardware, the software, the simulation training, all the technical pieces. But the final puzzle piece isn't technical at all. It's societal. How do companies prove this engineering is actually safe enough to deploy to the public, and for us to truly trust it? Well, they do this by establishing comprehensive safety cases. Waymo, for instance, utilizes a rigorous framework called the Case Credibility Assessment, or CCA. Because regulators don't just want basic safety reports, they demand a scholarly, methodology-agnostic argument proving readiness across multiple distinct layers. Layer 1 proves the brain and hardware are inherently safe and fail operational. Layer 2 proves the behavioral reflexes are sound, that the car makes the right decisions. And Layer 3 proves the overarching operational fleet can be managed securely out there in the real world. And to pass these stringent assessments, the vehicle's architecture must constantly prove its own reliability against strict diagnostic requirements. It continuously measures the timeliness, availability, correctness, and consistency of its own outputs. It's just not enough to be safe most of the time. The system must mathematically demonstrate that it meets the criteria of eliminating unreasonable risk every single time it boots up.
Which leaves us with this wildly provocative final thought. We've explored how autonomous machines use intermediate fusion to see in the dark, run parallel emergency maneuver calculations in milliseconds, and translate perfect digital training into physical reality. The sheer depth of this fail operational engineering is just staggering. It really makes you wonder, as these systems continue to evolve and scale, how long is it going to be before our own human hardware, our two eyes and our slow reaction times, becomes the actual bottleneck in road safety? Are humans destined to become the unreasonable risk? Thanks for joining me on this explainer. I really hope this helped you see the world of autonomous engineering in a whole new light.